Hi students, welcome to my channel Chemistry by PNSK. In this class, we are discussing about the quantum numbers. Today our topic is quantum numbers. Okay, before going to the main topic quantum numbers, we just take an introduction, which is this is the nucleus. Around the nucleus, many orbitals are there. Okay, around the nucleus, many orbitals are there. These are the orbitals 1, 2, 3 and so on. Okay, they are named as 1, 2, 3 and so on. These orbitals represents the size, shape, orientation. Okay, orientation. These orbitals are represents the size, shape and orientation of the electrons in an atom. Okay, how they are representing? By using the quantum numbers. Okay, if the orbital size is small, okay, suppose 1, its size is small compared to 2, then if you take the small orbital size which is nearer to the nucleus, at there finding the electron very easily. At there finding the possibility of finding the electron very easily. Okay, if number of orbitals are increasing, nothing but number of orbitals are more, there is finding the probability of the electron maximum. Okay, there is finding the probability of electron maximum. If number of orbitals are more, finding the probability of electron is maximum. Depending on these distinctions, the scientists are providing the quantum numbers. Okay, for each atom is explained by 3 quantum numbers. They are N, L and M. Here N is the principal quantum number, L is the azimuthal quantum number and M is the magnetic quantum number, and one more also there which is the spin quantum number. Okay, let us see how the quantum numbers are explaining the, let's see how the quantum numbers are provided explanation about the atom. Okay. The first quantum number is principal quantum number. Principal quantum number. Okay, the first quantum number is principal quantum number. It is provided by the scientist called Niels Bohr. Okay, it is provided by a scientist called Niels Bohr. The principal quantum number is denoted by the letter N. Okay, the principal quantum number denoted by the letter N. Next, in the principal quantum number, N is nothing but the number of orbitals. Okay, number of orbitals which is provided by the N. For finding the number of orbitals in an orbit equal to N. Okay, for finding the number of subshells in the orbit, number of subshells in an orbit is N square. Okay, what is given here? The number of orbitals in an atom is equal to N. The number of subshells in the number of orbitals in an orbit is equal to N. Okay, the number of subshells in an orbit is equal to N square. Okay, if we want to finding the number of subshells, then we are using the formula N square. Okay. Next, the angular momentum of the orbital is nothing but the NH by 2 pi. This is the angular momentum. Angular momentum of orbital, which is nothing but the angular momentum of the electron present in the orbital. Okay. For first orbital it is 1h by 2 pi. For example, second orbital it is 2h by 2 pi. For third orbital it is 3h by 2 pi and so on. For nth orbital it is nh by 2 pi. Okay, this is the angular momentum according to principal quantum number. Okay, next point. The principal quantum number explains about the size and energy of the orbital. Okay, size and energy of the orbital. Here, size and energy of the orbital is nothing but the presence of the electron in the orbital. Okay, next point. The n values are 1, 2, 3 and so on. They are represented like K, L, M, N and so on. Okay, they are represented like K, L, M and so on. Okay. Next point. As the number of n increases, size increases. As n increases, size increases. Here n is the number of orbitals. Okay, as number of orbital increases, size increases. Ultimately, energy of the orbitals also increases. Energy of orbitals also increases. Okay. Next point. This principal quantum number provides the total number of electrons present in an atom is equal to 2n square. Okay, total number of electrons are finding by using the formula 2n square. By using this formula, we are finding the how many electrons present in the orbital of the atom. Okay, each total number of electrons in an orbital is found by using the 2n square formula. Okay, by using this principal quantum number, the next quantum number is the azimuthal quantum number. Okay, azimuthal quantum number is explaining depending on the principal quantum number by the scientist called Sommerfeld. Okay, next see the azimuthal quantum number. The second quantum number is azimuthal quantum number. Azimuthal quantum number. Okay, it is given by the scientist called Sommerfeld. This azimuthal quantum number is represented by the letter L. Okay, L. L values are depending upon the N values. L values are depends on N. Okay, L values are calculated by using formula n minus 1. Okay, n minus 1. Next, this azimuthal quantum number was explaining about the shape of the orbitals. It is explaining about the shape of the orbital. Okay, this theory also explaining, this quantum number also explaining about the electron belongs to which subshell. The electron belongs to which subshell it is. Which subshell it is. Okay, in which subshell, as either S or P or D. Likewise, in which subshell electron is revolving is explained by using the azimuthal quantum number. Next one. This theory was depending on the principal quantum number. That's why this is explaining the energy order is S is less than, P is less than, D is less than and F. Okay, why? Because F is more energetic because number of subshells increasing, size of the orbital and energy of the orbital is increasing. that is provided by our principal number, which is dependent in by azimuthal quantum number. Next, the angular momentum of the electron was given by azimuthal quantum number is h by 4 pi into square root of L into L plus 1. Okay, L into L plus 1. Here, next point is L values are starting from 0. Okay, L values starting from 0, 1, 2, 3 and so on. Okay, these are the L values. But N values are starting from 1, 2, 3 and so on. Okay. Next, the number of subshells in an orbital is equal to N. In azimuthal quantum number of subshells in an orbital is equal to N. How many number of N values are there? That number is equal to number of subshells present in the orbital. Okay. By using these all, we are seeing the example representation of azimuthal quantum number is if n equal to 1, okay, then L equal to n minus 1, that is 1 minus 1 equal to 0. Okay, here it is a S subshell. S subshell. This azimuthal quantum number explaining about the shape of the orbital. Here S orbital is in spherical shape. Okay, spherical. Here the S orbital is in spherical shape. Okay, next, if n equal to 2, then L values are 2 minus 1, that equal to 1. L values are 0, comma 1. Okay, here L values are 0, comma 1. Then it is a P subshell. It is a S subshell. It is a P subshell. Okay. For P subshell, the shape of the orbital is dumbbell shape. Dumbbell shape. It is like this. The spherical shape is like this. Like this. Okay. Next. N equal to 3. L values are 3 minus 1, that equal to 2, which is nothing but the L values are 0, comma 1, comma 2. Okay. The subshell is D subshell. The shape of the subshell is double dumbbell. Double dumbbell in shape. Okay. Next, if n equal to 4, L value equal to 4 minus 1, that equal to 3, which are nothing but the 0, comma 1, comma 2, comma 3. Okay. Then it is the F subshell. F subshell. The shape of the F subshell is 4-fold dumbbell. 4-fold dumbbell shape. 4-fold dumbbell in shape. Okay. Likewise, azimuthal quantum number is depending on the principal quantum number, explaining the size and energy of the shells and shape of the subshells also. Okay. Please make a note of it. Here n equal to 1, L equal to 0. Here 0 also considered as a one number. Okay. If n equal to 2, L equal to 0, comma 1, these two are considered as n equal to 2. For 3, 0, 1, for 4, 0, 1, 2, 3, 0, 1, 2, 3. Okay, likewise L values are depending on the N values. By using N, we are finding the L by N minus 1 formula. Okay, next quantum number is magnetic quantum number. The next quantum number is magnetic quantum number. Magnetic quantum number. Okay, this is the third one. I forgot to give in the number, azimuthal quantum number 2. Okay, this magnetic quantum number was given by the scientist called Landé. The scientist called Landé. Magnetic quantum number was represented by M. Okay, M. And this magnetic quantum number was depending on the azimuthal quantum number. Okay, azimuthal quantum number, which is nothing but the L. Here you are observing one thing. L values are depending upon L values are depending upon N values. M values are depending upon L values. Okay, here the values of M are from minus L0 to plus L. Okay, minus L0 to plus L. From negative values to positive values are representing. Okay, the M values are calculated from minus L to L0 and plus L. Okay, here negative values are there, 0 is there and positive values are there. In principal quantum number, we are seeing from N values 1, 2, 3 and so on. In azimuthal quantum number, we are seeing L values from 0, 1, 2, 3 and so on. But coming to magnetic quantum number, we are including negative values also. Okay. Next point. If L values are starting from 0, L equal to 0, then M values are M equal to minus 0, 0, plus 0. Okay, likewise. Next, if L value is 1, then M values are minus 1, 0, plus 1. Okay, if L value equal to 2, M value equal to minus 2, minus 1, 0, plus 1 and plus 2. Likewise, if L value equal to N, then M values are minus N, 0 and plus N. Okay. Next, the total number of M values are equal to 2L plus 1. Okay, the total number of L values are equal to 2L plus 1. Okay, for L equal to 0, okay, if you take L equal to 0, M values are M equal to 2 into 0 plus 1. That equal to how much it is? 1. This 1 is nothing but the 0. Okay. Here this 1 is nothing but the 0. That 0 is S sub cell. Okay. If L equal to 1, then M equal to 2 into 1 plus 1, that equal to 2 1 ja 2 plus 1, that is the 3. Okay, here the 3 values of the M is plus 1, 0, minus 1, which is nothing but the p subshell. Okay, next, if L equal to 2, then m equal 2 into 2 plus 1, that equal to 5. The values of the m are minus 2, minus 1, 0, 1 and 2. These are the positives, these are the negatives. Okay, previous writing also correct, but for my convenience I writing this like this. Okay, next, the 5 orbitals subshell is d subshell. Okay, next, if L equal to 3, then m equal to 3 into, then m equal to 2 into 3 plus 1, that equal to 7. Here the values of m are minus 3, minus 2, minus 1, 0, plus 1, plus 2 and plus 3. The orbital is nothing but the f orbital. Okay, the orbital is nothing but the f orbital. If n equal to 4, the values are from minus 4 to 0 and plus 4, that is the z orbital. Okay, next, have you make a note? Here, magnetic quantum number signifies the orientation of the orbitals. Okay, it signifies the orientation of the orbitals. Orientation means in which axis it is. Okay, this is the nucleus of the atom. This is the nucleus. In which orientation the orbitals are located. Okay, either x-axis or y-axis or in z-axis. This orientation is explained by magnetic quantum number, and this magnetic quantum number also explains the number of orbitals in the subshells. Number of orbitals present in the subshell. If L equal to 0, m value must be 0. Okay, if L equal to 0, m value must be 0. That's why L equal to 0, then m equal to 0. If L equal to 1, m equal to, if L equal to 0, m equal to 0, the number of orbitals are 1. Okay, if m equal to 1, if L equal to 1, m equal to minus 1, 0, plus 1, the number of orbitals are equal to 3. Okay, if L equal to 2, m equal to minus 2, minus 1, 0, plus 1 and plus 2. The number of orbitals are 5. Okay, this is the S subshell, this is the P subshell, and this is the D subshell. Next, if L equal to 3, m values are minus 3, minus 2, minus 1, 0, plus 1, plus 2 and plus 3, then it is number of orbitals are 7. That subshell is called F subshell. Okay, F subshell. Understand? Have you got my point? This is the Px, Py, Pz. Okay, Px, Py, Pz. These three are the px, py, pz. Okay, the orbitals of d are dxy, dyz, dzx, dx square, y square, and dz square. Likewise, f orbitals also orientation explained by L values and M values. Okay, make a note on it. Okay, have you note all this? Next quantum number is spin quantum number. Our fourth quantum number is spin quantum number. Up to here, principal quantum number. Up to here, azimuthal quantum number depends on the principal quantum number. Okay, magnetic quantum number depends on azimuthal quantum number. But coming to spin quantum number, it has independence. Okay, our next quantum number is spin quantum number. Spin quantum number. Spin quantum number. It is denoted by S. Okay, it is denoted by S. It is proposed by Uhlenbeck and Goudsmit. The scientists are Uhlenbeck and Goudsmit. Okay, next. The spin quantum numbers are independent on the previous quantum numbers. It is independent quantum number, which means does not depend on anyone. The spin values are, for high spin value it is plus half, for low spin it is minus half. Okay, the spin value is high, it is represented by plus half. The spin value is low, it is represented by minus half. The angular momentum of the spin quantum number is h by 4 pi into square root of s into s plus 1. Okay, s into s plus 1. Here capital S is the spin of the electrons. Okay, next. It is explaining that the maximum number of electrons filled in the orbital is 2 with this is the orbital, this is the high spin and this is the low spin. It is represented by plus half and it is represented by minus half. Okay, here this plus half is the clockwise spin, minus half is the anti-clockwise spin. For clockwise direction it is expressing as a plus half, for anti-clockwise direction it is expressing as a minus half. Okay, by these conclusions of quantum numbers we are finding the number of subshells. By these quantum numbers we are finding the maximum number of subshells in a orbit is n square and the maximum number of orbitals in a shell is 2l plus 1. Okay, here n square is the number of orbitals in a shell. Orbitals in a shell. Okay, here 2l plus 1 is the number of orbitals in a subshell. Number of orbitals in a subshell. Okay, these are the quantum numbers for finding the size, shape and orientation of the orbitals in the atom. Okay, by these quantum numbers we are concluding the size of the orbital, shape of the orbital and also orientation of the orbitals. In our next class we are discussing the shapes of the orbitals. Okay. From these quantum numbers we are finding the number of orbitals, number of subshells, okay, maximum number of electrons in an orbit or number of electrons present in the subshells. Likewise the questions are asked in the competitive exams. Okay, for IPA exams also these quantum numbers are very important for 8 marks questions. If he asking the all quantum numbers, that is coming under 8 marks question. If he asking any one of 2 quantum numbers, nothing but the 4 marks question. Okay, for Andhra Pradesh students this year exam pattern is changed. Have you checked it once? The exam marks are for, the exam is conducting for 85 marks. In these question papers 1 mark questions also there, 2 marks, 4 marks and 8 marks. Okay, from quantum numbers any 4 marks question or 8 marks question is important. Okay, that's why you have to perfect them quantum numbers. Okay, from this he may ask 1 mark question, 2 marks questions, 4 mark question or 8 marks question also. Okay, thank you for understanding the class. If you have any doubts regarding the class or if you need any topic of lesson, you just ask me in the comment section. Okay, thank you, have a nice day.